Okay, class, what we're going to do is continue our discussion about properties of solutions by first revisiting oil and water miscibility. So what we have here is a diagram showing how energy changes over something like reaction progress. In the future, we're going to see a thing called reaction coordinate diagrams that shows how energy changes over time, or as reaction progress increases, as the reaction just kind of continues forward. What we have here is how on the y-axis, delta U, internal energy, is changing as different processes in dissolving or dissolution are occurring. And to remind you, delta U is internal energy, which is equal to our term Q, which is our heat energy, plus W, which is work. So first, if we start here at the bottom, at the beginning of our solubility, we have very little energy required to break up individual components of oil and oil. So those London dispersion forces, or just dispersion forces, are easy to break up, so this requires very little energy. The next step is breaking apart those hydrogen bonds, which requires a lot of energy. So an individual hydrogen bond is stronger than an individual dispersion force. In aggregate, however, since oil has really long hydrocarbon chains, it's very difficult to actually break oil apart, and it's overall easier to break water apart. And that's because water is just a single molecule bound to itself. It only has a molecular weight of about 18, whereas oil has these really long carbon chains that have really high molecular weights that can hold together better, similar to the Velcro analogy. So that's why we cook with oil. Oil doesn't evaporate. That's why we are able to dry off and evaporate water easily. But in any case, for the purpose of this explanation, we have very little energy required to break up a single intermolecular force for a nonpolar compound, and an intermolecular force is much more difficult for something like water. We then return and get back a little bit of energy from forming an oil and water interaction. So we have endothermic process. Endothermic process, increasing our internal energy, and then we release only a little bit. So overall, our internal energy goes up as this reaction goes forward, which is unfavorable, and that's why oil and water are not miscible. Now, if we consider another example, this time of ammonium and nitrate dissolving into water. Ammonium is our cation as it ends in IUM, and nitrate is our anion as it ends in ATE. So the dissolution is endothermic, and we know that because ice packs feel cold. The endothermic reaction is the system, and us, our hands, or how we're feeling it, we are the surroundings. So the reaction is taking heat from the surroundings, so it's taking heat from us, the person, so that's why we feel cold when we touch this thing. So why does this reaction happen spontaneously if it is endothermic? Well, here's why. We have a solute-solute interaction, so we have our ammonium nitrate. What we have to do there is break up an ionic interaction, and that's endothermic. Simultaneously, we have to break apart solvent interactions between water and water. Those are held together by hydrogen bonding. Breaking apart those is also endothermic. We then form a solute-solvent interaction, and that can happen two ways. The positive ammonium will be attracted to the partial negative charged oxygen. Oxygen's more electronegative than hydrogen, so it has more of the electron density. So that's that interaction there. Nitrate, conversely, is anionic, so it's more attracted to the semi-positive charge hydrogen. So remember, a lot of the electron density is on the oxygen, so that makes hydrogen a little bit more electropositive. These are interactions that are forming, so it is exothermic. They are releasing energy. Overall, the reaction is endothermic and feels cold. So why in the world would that be happening? That has to do with our two criteria for the formation of a solution. Generally, we're trying to decrease energy of the system. So a decrease in energy, so when we have a delta U is negative, that's really favorable. We're also trying to increase disorder entropy. That is not always predictable. So here, it's really difficult to predict that, that these types of reactions would increase or decrease entropy. Sometimes you have to simply make an observation to determine whether entropy is increasing or decreasing. This is an endothermic reaction, which is not spontaneous, but the reaction is happening anyway. So if we have an increase of input of energy that's necessary for the reaction to happen, there must be a driving force for that reaction. Typically speaking, endothermic is not favorable, so the only driving force that's possible here is that we have an increase in disorder entropy. Now let's define solubility. So the solubility of a solute in a particular solvent is equal to its maximum concentration. So we can qualitatively say sometimes that something like sodium chloride is soluble in water, or sodium acetate is soluble in water. But when we're talking about its solubility as a noun, it is defined in terms of how much of that compound can go into the solvent at a certain temperature. So for sodium chloride at 20 degrees, that's 1 molar. So that is one way of describing concentration for a solubility. That's molarity, which is, of course, moles per liter. Solubility also has a particularly unique unit called, which is sometimes expressed as grams per 100 milliliters, which we see with sodium acetate. So sodium acetate, described with OAC, its solubility at 20 degrees in water is 123 grams per 100 milliliters of solvent. If we are considering a spectrum of solubility, we are saturated at the point of solubility. Anything less than that and we're undersaturated, anything over that and we're supersaturated. Acetate is the anion OAC, and here's the Lewis structure for acetate, OAC. Now let's talk about solutions of gases in liquids. So the chemical structures of compounds and molecules and the resulting intermolecular forces really determine how much of the solute can go into the solvent, because we got to really make sure that these interactions are favorable. So let's take a look at 3 different molecules or elements. Ar, which is argon, the noble gas, O2, which is dioxygen, and CH3, which is chloroform. Chloroform has this formula here, where we have a central carbon and 3 chlorines that are attached with 1 hydrogen vertically. We have 4 substituents in a tetrahedral geometry. Chlorine is more electronegative than carbon, so we have a dipole arrow along each carbon-chlorine bond, so showing that it is a polar covalent bond, pulling electron density away from the carbon. We don't have a dipole arrow along carbon and hydrogen because we consider that a nonpolar bond, as the difference in electronegativity between carbon and hydrogen is only 0.4. So overall, we have 3 polar covalent bonds. This is an asymmetric molecule, and we see that more electron density is going down, so we have an overall dipole moment. The intermolecular forces for each of these compounds are as follows. Argon is a dispersion force, it's nonpolar. Dioxygen is also nonpolar, so it has dispersion forces. Chloroform is polar, and so it has dipole-dipole interactions. This is not capable of forming the special type of dipole-dipole interactions called hydrogen bonding, because that only works with hydrogen on particular elements, and carbon's not one of those. Within the 2 different non-polar compounds, we can actually specify a little bit more in terms of their polarizability. Argon is less polarizable, it's smaller, and it's just a sphere of electron density. Dioxygen is more polarizable because it's a molecule, it's more than 1 atom, and so it's spread out over a larger area. The only thing that allows molecules capable of dispersion forces only from sticking together is this separation of charge density that can happen occasionally. That's it. If you have a larger molecule, you can get a little bit more separation. If you have a smaller molecule, smaller separation. So dioxygen can stick to itself better than argon, but overall, both of them are pretty bad at sticking together, whereas chloroform is better at sticking with itself. The solubility of gases is also affected by the partial pressure of the solute, and we describe that using Henry's law. The quantity of the ideal gas that dissolves in a certain volume is proportional to its pressure. And so here's the equation. C sub G is equal to K times P sub G. So C sub G, C being the concentration, G is the gas. The solubility is either going to have units of moles per liter like molarity, or these special units, grams per 100 milliliters. Fancy K is the proportionality constant, and that depends on the gas. Its units are concentration per pressure every time, and they should match C sub G. So if your concentration, your solubility, is moles per liter, then you want your K, proportionality constant, to also be moles per liter. If your solubility is expressed in terms of grams per 100 milliliters of solvent, then you should also have your proportionality constant be grams per 100 milliliters. P sub G is the partial pressure of the gas. So when we look at gases being dissolved in solvent, an interesting thing happens in that the solubility is inversely proportionate to the temperature. So as you increase the temperature, as we go from left to right across the x-axis, the solubility of these gases actually drop. You have methane coming down, dioxygen dropping, carbon monoxide dropping. So the amount of gas that you have in solution decreases as temperature increases. The reason for that is because kinetic energy is increasing as temperature increases. So temperature increases, the kinetic energy of the gas increases. That results in having a higher pressure as a result of more gas escaping the solution. Conversely, if you were to look at solids, most solids increase in solubility as you heat them. So for example, sugar, the more temperature you add, the more thermal energy you add, the easier it is to dissolve. It's a lot easier to dissolve sugar in hot water like tea or coffee than it is to dissolve it in ice water. So let's look at an example using Henry's law. So if you have 100 milliliters of water at 0 degrees Celsius and you're able to dissolve 1.45 times 10 to the negative 3 grams of solute at 152 torr, we can then use those conditions to figure out what the solubility of the gaseous solute is at 760 torr. So let's figure that out in a two-step process. The first step is taking our Henry's law equation, C is equal to K times P. We have C at 152 torr. That's 1.5 times 10 to the negative 3 grams. So we have 1.5 times 10 to the negative 3 grams divided by 100 milliliters of solvent, because that's given in the problem, dissolved in. And that's going to be equal to our proportionality constant K times pressure, which is 152 torr. If we solve, we get K is equal to 1.5 times 10 to the negative 3 grams per 100 milliliters divided by 152 torr, or times 1 over, which is equal to 9.5 times 10 to the negative 6 grams per 100 milliliters per torr. I rewrote these units as the inverse because we should also be comfortable seeing units as being inverse units. So we now have a value of our proportionality constant. It is in grams per 100 milliliter so that it matches our C, our solubility. We then take those conditions using the proportionality constant K and change our pressure to 760 torr. When that happens, we get a new solubility, which is what we're solving for. So we take K, which is 9.54 times 10 to the negative 6 grams per 100 milliliters per torr, multiply it by 760 torr. The units for pressure cancel, and we are left with our solubility, which is 7.25 rather, times 10 to the negative 3rd grams per 100 milliliters. It's really tough sometimes to ignore that 100. All of your training tells you to divide by that and get rid of the numbers, but for solubility, that must stay because that is part of our units. And finally, we are going to have a quick conversation about solutions of liquids and liquids and of solids and liquids. So liquids that dissolve into one another are called miscible. So a common example is water and ethanol. A phrase to describe solubility of liquids in liquids, or rather their miscibility, is simply like dissolves like. And if you've heard that before, that is discussing polarity. A like type of polarity will dissolve another similar type of polarity. So for example, polar things dissolve other polar things. And the reason for that is we have forming favorable solute-solvent interactions at the end of the process. So after you break apart the water and after you break apart the solute ethanol, they come together to form an interaction between the solute and the solvent that is very favorable. And for this example, that favorable interaction is the formation of a hydrogen bond. That's a stable bond. The more stable bond you're forming, the more energy is being released, and the lower the energy of your system, the more favorable the process. Liquids that remain separate and do not mix are called immiscible, as we've talked about, oil and water. Solutions of solids and liquids. Generally, as temperature increases, the solubility of solids also increase. More energy is provided for breaking solute-solute interactions. So as temperature increases, your thermal energy is increasing, and that allows you to overcome this endothermic process of breaking the solute-solute interactions more easily, and you get graphs like this one that we were just looking at, where we have most solids increasing in solubility as we increase the temperature. And that is it for today's lecture material.